Hi, welcome back to Imperium Learning. In this particular video I'm going to be covering how to apply the Perron unit root breakpoint test in Eviews. Before I actually show you how to do it on Eviews, I'll probably spend the next 5 minutes giving a bit of background information which will help you understand why we applied the test and also when we apply the test. So just looking at these first two paragraphs that I've got here on this slide in front of me, to answer the question why we conduct unit root tests in the first place, it's basically because if we don't do that, then we expose ourselves to the risk of conducting regressions with non-stationary variables which result in spurious regressions. So spurious regressions in this case would lead us to reach conclusions about our data which is false. So we want to avoid that. We want to have good quality research and we want to make good conclusions. So when we want to produce good research, then we should always be applying unit root tests first. Also, to answer the question, why do we even have to apply unit root tests which allow for structural breaks in the data generation process as opposed to just an ordinary unit root test like, say, the augmented Dickey-Fuller test? Well, it's essentially, and again I've written the answer there, failure to do so creates the risk of falsely accepting the null hypothesis that a unit root exists when the DGP is merely a trend stationary process with a structural break. So what does that mean in practice? It means that if you're applying an ordinary unit root test like the augmented Dickey-Fuller test, it's quite likely that it increases the probability of having a p-value that's above 0.05, and because the p-value is above 0.05, it won't be able to reject the null hypothesis that there's a unit root present in the DGP. So a unit root test that allows for structural breaks will increase the likelihood of having a p-value that's below 0.05, and therefore we'll be able to reject the null hypothesis when your DGP is merely a trend stationary process with a structural break. So just going forward, this is a good follow-up unit root test to apply if you've first and foremost applied the Chow structural breakpoint test. It wouldn't really be an appropriate test to apply for a structural break test where the breakpoint dates are selected endogenously. That would be more a case of the Lee-Strazakic test. In a future video, I'm going to be showing you how to apply the Lee-Strazakic test, but not now. Just bear in mind that if you're analyzing a variable, do the Chow breakpoint test first, and then do this Perron unit root breakpoint test next. Here's the actual format of the equation for the unit root test, right there. And also, if your model does not include an intercept break, set alpha 1 to 0. Alpha 1 is there. If your model does not include a trend break, a trend is a time trend, set alpha 2 to 0. So this whole thing would become 0 then. And so again, here's a brief little summary of the null and alternative hypotheses. This Greek letter here is pronounced psi. Okay. So the null hypothesis is that psi equals 0, and that the alternative hypothesis is that psi is less than 0. Notice how it's a one-sided test, by the way. pay particular attention to that. So basically, we want our variables to be stationary, and because of that we'll be hoping to have a p-value which is below 0.05 for this test. We want a p-value that's below 0.05. If it's above 0.05, that probably means it contains a unit root, and in that case we'll have to difference the variable before doing any regressions with it. Finally, I've just added this point here. This actually happened to me in one of my pieces of coursework, that's why I've decided to include it, which is, what if even the first difference, okay, imagine this, imagine you do a unit root test on your variable and it can't reject the null hypothesis, so that means there's a unit root, and so then you difference it and then you apply the test again and it still can't reject the null hypothesis because the p-value is still above 0.05. What are the implications of that? Well, my advice is that in general it's very, very rare that you have data that's integrated to an order of 2. That's what this notation means here, integrated to an order of 2. That means there should be integrated to an order of 1. It's most common for time series data to be integrated to an order of 1, very uncommon for data to be integrated of an order of 2. So if you find that, the short answer is that you've probably specified the test role. So make sure that you experiment a bit with your test specification, and hopefully you should get results which imply that it's integrated to an order of 1. And so finally, just before we apply the test, I'm just going to tell you a bit about the lag selection method for the test. Basically, the original unit root breakpoint test, which we're covering right now, that was originally published in a paper dated in 1989, but I found a paper published in 1997 by Perron, same author, who recommends using an f-test because he found that using information criteria like a Schwartz information criterion can suffer from size distortions when dealing with time series data. So as a result, we're going to apply a slightly modified version of the original Perron unit root breakpoint test. So going on to Eviews then, okay, let's just cancel that very quickly. Let's look at, in fact, I can actually see that I'm getting very close to the 10-minute mark now. I'm actually going to be using 2 examples because I've actually got 2 very good examples to show why this test is important, and so as a result I will actually be applying the tests on Eviews and showing you how to interpret the output results in a second video. So I'm going to wrap up the video now, and I will show you how to do the test in a second video. Okay, bye now.